Hi everyone, I wanted to talk for just a minute about solving systems of equations. I've had a couple of emails asking me about 3x3s and how do you solve three equations, three unknowns. And before you can do that, you kind of need to look at two equations, two unknowns. So what I have here is the possibilities of what happens when you have two linear equations on a Cartesian coordinate system. The first case that can happen is if the two lines are parallel, meaning they have the same slope, then since they don't intersect, we'll have actually no solution to this problem. Parallel lines never intersect, so there's not going to be an XY solution for that particular situation. The other situation that we have, case 2, is the two lines do indeed intersect, so we get one solution, and that solution would be represented as an ordered pair. Another case that we have is the case of the exact same line. If the two lines are just multiples of each other, and it's indeed the same line, then what you're going to see is a graph where each line falls on the other. Now, when we solve the equations and we get these two cases here, something very interesting happens. Here's a 3x3. I'll show you and work it, and we're going to get one of these interesting solutions. Here's a problem that was sent to me by a student, and what we have is we have three equations, three unknowns, x, y's, and z's. Now the second equation is missing an x value. If I want to solve this equation, I can't solve simultaneously three equations, three unknowns, but I know for a fact that I can solve two equations, two unknowns simultaneously. So what I want to do here is I want to use equation number 1 and number 3 to get my x's to add out so that all I'm left with are y's and z's, so that I can use equation number 2 in order to help solve for either y or z. The way that I'm going to do that is I'm going to take equation 1 and I'm going to multiply it by a -2. If I multiply equation 1 times -2, here's what it would look like. And if I multiply through with the -2, I'll get a -4x minus 2y plus 4z equals -6. Now what I'll do is take equation 3, line it up underneath here, and add the two equations together. That should give me only the y and the z left over. If you notice, the 4's add out to become a 0. Positive and negative 2y, positive 3y, that'll give me a positive 1y minus 3z equal -12. Now I have what's called new equation number 4, and I'm going to try to get something to add out, eliminate one of those variables with equation number 2. Probably the best thing to do here would be to decide which one do you wish to cancel out. Now, if I take equation number 4, and if I multiply it by a -1, a -1y and a positive y would indeed give me a situation where the y's would add out to become 0. So I'm going to multiply by -1, so I'll get -y plus 3z equal positive 12. The y's indeed add out to become 0, but what interestingly happens here is the 3z's also add out to become 0. 12 plus 4 is 16, so I end up with 0 equals 16. This is a false statement, and since it is a false statement, I'm going to have to conclude that these three lines in a three-dimensional space do not intersect each other.